And today I will be presenting hybrid autonomous intersection management for minimizing delays using fuzzy logic. This will be the outline. We'll have an introduction, and then we look at the high-level approaches of controlling an intersection. Then we'll look at the problem statements, the research objectives, some contributions, and then proposed solutions, results, and then we look at some conclusion. Now, traffic delays are a necessary part of life that are undesirous. We really don't want to wait at any point. When we come out, we just want to go. I remember this morning when I was trying to use the elevator and I pressed the button and then I had to wait for some probably seconds. I was feeling, oh, this is too much. Why do I have to wait? I wished at the press of it, the elevator should just open up and then I go in and then move me to where I'm going. But then it is usually not the case. Why? Because we have so much demand. Like the speaker said earlier this morning, demand is not equaling supply. Now, statistics have shown that vehicular registration has this pattern. You can see here in Canada, in fact, in the first quarter of this 2024, over 400,000 vehicles have been registered. And what does that tell you? It tells you that we have more vehicles than the infrastructure can take. So, another report has shown that in cities of Canada, that shows the time delay as you travel, with Toronto having the highest with an average time of 50 seconds compared to the 2022 statistics. And on the average, you lose about 98 hours in transit. I mean, that is a lot. So that means that we have need to continue to look for ways to minimize these delays as much as we can. Now, like I've said, usually these delays happen because we have intersections where vehicles have to merge and dispatch and all of those, and we chose to liken it to a kind of a funnel, because you have a lot of vehicles, and if of course the infrastructure has the capacity to contain these vehicles, they are most likely going to be moving with very minimal delays if there will be any. But then it is not always the case, because we have to connect from one point to another. Now, if you say that, okay, we can connect a route from one point to another, then it would mean, of course, if you think of it from the perspective of a graph, that in fact it is impossible, right? Because of the cost associated with building this infrastructure and what have you. Now, because we have intersections, we want to find ways to control intersections. So there has been a couple of approaches that has been adopted in literatures and of course in real life to control these approaches, intersections. The major way is a decentralized approach. That means we place our controller at the intersection, and this is the principal thing that manages traffic around the intersection. Now, it is flexible, so if you look at your traffic lights, for example, if this traffic light is controlling the intersection independent of other stuff, then we can refer to that as a centralized controller. Now, the challenge with this is that it has a single point of failure. Should there be a problem with that controller, then what happens? Automatically the system shuts down. So it is not actually serving, it may not always serve in all cases. Now we have the decentralized approach. Now in this approach, which is found mostly in the literature currently, you will find that vehicles have the capacities to talk to themselves, and so by exchanging their state information, vehicles will naturally have a way to plan out their trajectories such that they utilize the intersection with minimal risks. Now, this is very suitable when the traffic volumes are less. However, it becomes a big challenge when volumes increases beyond capacity and all of those. So we still are looking for ways to optimize these and minimize delays. Now, because of the downsides of the two approaches I've mentioned, the centralized and the decentralized approach, there has been another class which combines these two to kind of take advantage of the different approaches, which is the hybrid approach. Now, you have a centralized controller talking to vehicles in a way these vehicles are able to talk to themselves, and then of course the centralized controller schedule vehicles on how to navigate through the intersection, and then of course the vehicles also exchanging information can effectively, hopefully, because if I say effectively, authoritatively, it may not always be true. So they communicate in a manner to find ways to also navigate the intersection in an optimal way, while also hoping to enhance safety. Now, this also works to a large extent, and so this is the path we have taken. Now, to the problem statement, which we already have laid the foundation about it. The problem is traffic congestion, which we don't like, which has a lot of implications, like the presenter would say today, that little delay, you find drivers growing impatient and they tend to shout on each other. I've seen this more in African setting. I'm from Africa, I'm from Nigeria. A little delay, you can find people talking on top of their voices. You hear the honking and all of those, and it's crazy. Now, it has implications on economics and, of course, social lives and what have you. These are things we are not desirous of. And so we are interested in minimizing the unnecessary delays that we experience while commuting. So the aim of this research was just to minimize traffic delays at an isolated intersection. However, not just minimizing the delays, but also ensuring that the throughput is also enhanced. So, and then the objective was just to implement a physiology-based control, centralized controller, and then also implementing a decentralized controller in a way to combine take advantage of the centralized and the decentralized approach. So the contributions of this paper is twofold. We designed and implemented a physiology-based controller, and then of course we integrated the same with a V2X technology, which is to come. We of course have some implementations here and there, but we are more futuristic probably, and so we're interested in that, so we integrated that in the implementations. Now this is the proposed solution, and this is how our architecture look like. We have the vehicles, which are independent anyway, even though we put them in a box, they are actually independent vehicles. They, in themselves, what we refer to as the centralized controllers, that means these vehicles can implement decisions of their own. Then when vehicles want to talk to each other, they use a V2V communication approach, and in this case, we are using an intersection collision avoidance message. And then you have vehicles communicating with the centralized controller, which is the, say, for example, a traffic light, in what using what we refer to as the signal request message. And then, of course, the centralized controller communicates schedules to the vehicles using the signal phase and timing message. Now, the centralized controller has a message signal processing request message processing unit, and then we have the communication unit, and then of course the traffic control algorithm that makes the decision of which approach is scheduled, which vehicles are scheduled, and those. And because we are looking at the situation where you could have autonomous and non-autonomous vehicles, that is human-driven vehicles, automatically we are integrating them with normal traffic lights in that manner, so as to enhance this movement for all classes of vehicles. And that the decision of how long a given phase should remain is taken by the physiologic control. Now the V2X communication, we use a side standard. So we have the SRAM message format, which communicates the vehicle ID, the timestamp, the junction at which the vehicle is wants to utilize the intersection, and then its approach leg, its depart leg. That way we can tell if the vehicle is turning left or right or going straight through, and then the vehicle type. That will give us an idea of how large or the dimensions and other behaviors of the vehicle. And then its geocoordinates as well as the arrival time. And arrival time in this context is when it arrives at the traffic junction, and that we define as 100 meters away from the stop line of the approach. Now, its own priority also, because not in this work, we are also trying to implement another one that considers the priority. Here we have a flat priority. And then the message type. This message type is just to tell us if the vehicle is departing or is approaching, because we want to take out vehicles that have utilized the intersection, and that's why we introduce that. And then we have the intersection collision avoidance with those attributes, and then the signal phase and timing message, which is from the centralized controller to the vehicles, and they can take decisions based on that. Now, we show the algorithm which we implemented for each of these. The centralized controller, essentially, the way we implemented it is just to ensure that we minimize the chances of traffic collision at the intersection. And for that, we use the timed collision avoidance in that context. And then the centralized controller was implemented such that we determine which approach will go at what phase duration. So this is the fuzzy logic component. We have 4 inputs, and then the output is the phase duration, and of course the input will be the queue length, the waiting time, the speed, that is the speed of the vehicle, as well as the distance from the intersection, right? And those are the parameters. And we use the triangular membership functions to model this because they are flexible and they are computer efficient to a large extent. So that is the whole idea. Now, to test what we have done with we implement our approach on an isolated intersection, and we divide the intersection to 2 regions. That is the intersection zone, which is for this we consider that at 100 meters away from the stop line of an approach, and then from 5-10 meters into the intersection we consider it as the critical point. Why we did that was to minimize the number of messages that can be transmitted, to avoid collision and all of those loss of messages. So a vehicle transmits an SRMM within the intersection zone when it is within the intersection zone, and when it is at critical zone, it transmits an IC, meaning it has been scheduled to utilize the intersection, but then we want to avoid situations where vehicles could collide, possibly because maybe an oncoming vehicle couldn't brake and it is still going into the intersection, and then another has been scheduled. So we want to avoid that possibility. So that is where the decentralized control actually works in this research. So now we use the active mosaic for this purpose, which allows us to model the vehicles and commute, as well as which provides us with communication facilities to be able to communicate, and we use Java Fusilite to implement the scenario, the fuselage component. Now, to run our simulations, we use these flow rates, the 100, 200 on 2 ways, and then we have the 4 ways that follows that, and these are the rates of the tones. This is numbers, I mean, the number of vehicles, tone, and all of that. And the flow rate is at kilometers, number of vehicles per hour. So we haven't done that. We ran the simulation, and this shows the results. Now, from the results, we can see for delay, we were able to achieve a better performance compared to others. The fixed time controller, as well as a recent research published by Zhu et al. Which you can see from here, we had about 35% reduction compared to the static approach of 25 seconds, and then the 30 seconds, as well as the Zoom. So for Zoom, which is a recent one of the recent published work, we achieved better performance by 16%. And then For the throughput, we achieved 12% better performance, and yes, that is that. So for this, we have proposed a fuselage-based autonomous intersection control, which we might achieve minimal delay by about 16% and 12% in throughput compared to a recent published work. And we want to extend this approach to multi-intersection scenario and see how it will work, as well as consider a number of other stuff, because you can see from the message, there is some SRM message. You can see there are a number of things that we actually didn't use, so we hope to explore more in that direction. Thank you.
Thank you, Zachariah, for the presentation for the paper and minimizing delays using fuzzy logics. So we have about a minute room for questions. Any questions? Okay. Thanks all once again. Thank you all for attending today. I hope the session was efficient. Thanks all for your time.